Good morning, good afternoon, good evening, dear participants. This is the last day of the World Resources Forum conference, and we have today the online sessions with scientific presentations. I am very pleased to host today a very nice composition of panelists that will enlighten you on the topic of circularity in critical raw materials and battery value chains. So we will start with the first presenter, Juan Pablo Esquivel from Fuelium and BC Materials in Spain. Juan Pablo, the floor is yours. You will provide the title of your presentation, and you have 7 minutes to present. Thank you.
Thank you very much, Sonia. Just before I start, well, I just want to thank the opportunity to present here in this online version of the conference, even though I couldn't join this week. Well, excellent. So good morning and good afternoon and good evening, everyone. I'm Juan Pablo Esquivel. I'm an Iker Basque associate professor at BC Materials. I'm also co-founder of a spin-off company, Fuelium. And today I will share some of the work that we have been doing on eco-design, batteries, and devices that have been doing in Barcelona for almost since we started about 20 years ago, and that now continues in Bilbao since we moved 4 years ago. At our research group called EDGI, we develop power devices and systems using eco-design and circular systemic thinking, and we aim to consider doing this considering the biophysical boundaries of our planet and the social outcome. We propose a methodology to eco-design batteries that can follow the life cycle of the product that they are powering. A concept that we called fit-to-purpose batteries, because we, starting from the use, we apply a holistic vision of the product and take design decisions that minimize environmental footprint at every stage. With this, over the years we have reported several examples of these batteries. For example, batteries for smart packaging, batteries that can be recycled with paper or cardboard, or batteries, biodegradable batteries for places where there is a lack of battery recycling infrastructure, or batteries that are inspired in plants or flowers and that can be composed and come back to nature in the same way a plant does after the end of its life cycle. Or batteries for disposable diagnostic devices that have resulted in the technology that is being commercialized by the company Fuelium, which I will introduce in more detail now. Fuelium is a startup company that was founded by myself and other co-inventor of the technology, together with two partners with experience in the biomedical sector. The company was created to provide a sustainable solution to the need of power in disposable diagnostic devices. Devices such as this one, a digital pregnancy test. It's a wonderful piece of technology that is providing a lot of convenience, rapid and easy to read results to the user. But with the cost of having electronics, LEDs, sensors, photo detectors, and an LCD screen, everything powered by a lithium coin cell battery that is going to be used for 3 to 5 minutes, and then it's probably going to be disposed of uncontrollably. So this made us think in an alternative power source that could be more compatible with the life cycle of these type of products. So we created a paper battery that works in the same way as the lateral flow assay. It is activated upon the addition of a liquid in one of the extremes of the strip that flows by capillarity, triggering the generation of electric power. And this liquid can be plain water or the same biological fluid that is to be analyzed in the device. With this, we have a unique value proposition for batteries for the disposable diagnostics, which use materials that are the same safe and medical grade materials. They're using already cost-efficient and scalable manufacturing processes. And then it has different unique features, such as this is a battery that is only activated upon the addition of a liquid, so it doesn't have self-discharge. So this would provide an unlimited shelf lifetime. And also we can scale the size and the power and the specs of the battery to the requirements of the application. Also, we have make sure that this battery can actually follow the end of life for these devices. So this battery can be incinerated without the risk of explosions or creation of toxic gases, recycled with paper cardboard, or even composted. Inspired in this lateral flow test strip. So our batteries have the same materials, design, and manufacturing processes. So we have batteries in formats of strips or rolls that then can be cut to the desired width depending on the needs of the application. With this, we have powering different the typical functions required in these type of devices, such as electronics, telecommunications, or temperature control, and even use this to create a molecular diagnostic demonstrator that is using our power source, a minimalistic electronic circuit, has been tested in clinical environments. Just to wrap up, we believe that this type of fit-to-purpose minimalistic approaches based on the principles of sufficiency would be the way to go to reduce materials, energy consumption, and e-waste generation. And in this way, provide real solutions to the needs in the point of care that are economically viable and environmentally sustainable. So with this, I'll just want to thank you, and I'll be happy to answer any questions. Thank you.
Thank you very much, Juan Pablo. Very interesting. Of course, we may have some questions. I think we will have a really good time for discussion with the presenters. So unless there is a burning question that I did not see in the questions and answers box, yes, there is one burning question. So let's address this and then we continue with the next. But there will be more questions at the end. Are those batteries in general rechargeable? What materials do you rely on?
Yes. So for these applications and the technology that we already have developed and in a commercialization stage, these are primary batteries because these type of products are typically single use. So once the biological sample, the urine, sweat, saliva, blood, any of the biological fluids, it's included in the test. This test cannot be reused again. So the same way as the test is the same strategy that we're following for the battery. In parallel, we're also working in different battery chemistries that could provide also solutions for a reusable test. But these are still in a lower TRL. And yeah, the
Excellent.
materials so they are proprietary, but I can say that they are abundant, non-toxic, and renewable materials.
Excellent. So I think there are more questions, but let's leave them for the end, okay? We continue with the next speaker. And please, thank you, and a virtual applause to Juan Pablo. And please, the next speaker, Silvia Boba. And we'll continue presenting on critical raw materials, rich products, and very important topics around this. So Silvia, the floor is yours.
So thanks a lot for this opportunity to present our work. Before entering in the detail, I would like to spend a few words on what is the Joint Research Center is. So the Joint Research Center is a part of the European Commission, and it provides independent, evidence-based knowledge and science to support concretely the EU policies to have a real impact on the society. There are different sites of the JRC. The headquarters is in Brussels, but there are 5 sites located around Europe, and in particular myself, I'm located in Italy, which is the biggest center right now. So to enter in the topic, this is what I would like to present. So a short introduction, then I will focus on the main challenges and key aspects of the circularity of materials. And I will enter a bit more in the work we developed about waste batteries available for collection, highlighting some lessons learned, and then some perspectives and conclusion. So everybody knows that critical raw material and strategic technologies are essential to increase the sustainability of goods, products, and globally decarbonize the society. As a consequence, we are expecting a fast increase of the demand of technologies like batteries, wind turbines, photovoltaics, and so on, which is associated to a fast increasing demand of materials. And inevitably also related issues with the supply of materials and EU resilience. And this is very well highlighted in the last foresight reports published by the European Commission, and for sure the European Critical Raw Material Act in force since 2 years already. Speaking about batteries, it is worthy to notice that the battery regulation is taking in consideration also materials in the regulation, and it is a very life cycle based approach regulation. What you can see here is the life cycle of the batteries that is almost all covered by the regulation. And the reports you can see, and then in the presentation you will find the links of the reports, are the reports that are results of the work that the JRC from different sites is developing to support the regulation, from the carbon footprint to recycling, collection, safety aspects, removability, and so on. To be ready for the future, which is very important in our work, information on the type and volumes of new products that will become very soon waste products to be properly managed is essential. It's also important to identify the new opportunities in the market, and remanufacturing, as highlighted in the slide, or repurposing for batteries is something that needs to be considered, and it's very important. And the third thing that is very important is the validation on the proposal and scenario, because as you know, there are a lot of models trying to estimate the future demand of materials, but data behind need to be really validated, and also scenario need to be validated. And I would like to highlight that stakeholders of the whole value chain of batteries needs really to be involved in this process. To be ready for the future, clearly we need to adopt scenario analysis and forward-looking analysis to monitor the current strategies, but also to prioritize the strategies according to the objective that we want to achieve. And we need to have future-proof measures, and targets is really a clear example on these targets. For instance, on recycling, recycled content materials, collection in this case. So let's enter really on the work we developed. If circularity is the way to improve sustainability, for sure is absolutely necessary to map well where and when materials will be available for recycling or for different other circular strategies. So the first step of the work was really to identify and to study in depth the system of batteries. We develop a very detailed material flow analysis, and since the literature is quite incomplete, which is very simple, the reason is that there are new technologies like e-bikes or light means of transport in general, but the demand is really expected to pop up, is already doing. So the literature is incomplete. So we carried out a set of workshops involving recyclers, sorters, manufacturers, companies, OEM, association, member states, and we visited plants to really better understand the reality and then to translate it into a material flow analysis that can cover what is happening and what will potentially happen in Europe in the next years. We then developed a forward-looking analysis considering different scenarios, validated by the stakeholders, as I mentioned before, and we have a huge amount of data. Based on all this work, the JRC proposed a methodology to have future-proof, but also an ambition and workable collection targets, which is really essential to provide enough materials for the next phase of the life cycle, which is clearly, I mean, not necessarily, but is recycling, and I will enter in the detail. So we had the zoom on the collection, but it's clearly for us that the collection is not disconnected from the rest of the life cycle of batteries. If we focus on the whole life cycle, we can see that the collection can for sure provide materials, let's say product to the recycling, and the recycling and recycled contents target are pushing for maximizing the collection. But it's also true that other aspects related to other circularity strategies like repurposing, like remanufacturing, lifetime, are really pushing this available for collection. So to conclude, I would like to highlight three main concepts that were really the added value of our work. The first concept is that circularity should be conceived as a framework, so collection between the strategies should be fully understood and taken into account in the analysis. In an environment where data are lacking and technologies are evolving, input and practical knowledge that can come only from stakeholders along the whole value chain is invaluable, and this is really the added value of the work we are developing at JRC. And for sure, batteries is an example, but batteries are not the only critical raw materials rich product. So the approach and the lesson learned can for sure be useful for other type of products. Vehicle regulation is an example. It's not anymore an end-of-life vehicle directive, but it's a vehicle regulation, so life cycle based approach again, but also for the WE regulation, which is very linked to the eco design regulation, and again, they are adopting a life cycle approach. With this, I thank you, and I'm available for sure for questions if needed. Thank you.
Thanks a lot. Maybe there is time for a burning question. Should an end-of-life battery have the legal status of a product rather than a waste? It's in the chat.
Yes, very good question and very long discussion. I started working on batteries since the review of the batteries directive, and this is one of the main novelty of the battery regulation is really the repurposing, the introduction of repurposing and remanufacturing concepts. And in our model, we consider two different model and also the report of available for collection. We consider two types of repurposing from a legal perspective and two types of remanufacturing, because repurposing can be applied to batteries that are not yet waste, so they are not yet collected. So you can apply repurposing remanufacturing to a battery product. But also after collection, you can apply remanufacturing and repurposing, and it's called the preparation for remanufacturing and preparation for repurposing. This is the legal name. So you can also address waste batteries to preparation for reuse, remanufacturing, and repurposing. So there are a lot of opportunities. I know that it's difficult, but I feel that reading the regulation in the case of batteries is really, really interesting. But yes, in the reports that we are publishing, this is a very important point, especially for collection, because it's in the middle, for sure.
Thank you. I think we'll have more questions at the end.
Okay.
Thank you. And we welcome the next speaker now. And he comes from Australia, if I am not mistaken, with the sequence. Yes, exactly. So welcome, Stefan Northy. And please, the floor is yours now with your presentation.
Thank you so much, Sonia. I guess just before I get started, I'll just let everyone know that I'm making this presentation on behalf of Damien Jerko, who was unfortunately unable to attend today. But he sent his regards and obviously he hopes that the session goes very well. So what I'm going to be presenting on is some work we've been doing in Australia as part of a large cooperative research centre that was established back around 2019. And that's called the Future Battery Industries Cooperative Research Centre. And so within that overall research centre, we had a project that was looking at both certification and also life cycle assessment of battery materials. And it was a large collaborative project. I guess just to set the stage, I guess it's probably not news to anyone, but in the future, we're expecting fairly large growth in both the use of batteries for electrification of the economy and for electric vehicles. And as part of that, that's driving a lot of demand for materials. And most of that demand in the short term is going to come from mining. So as we kind of scale up these industries, we've got a lot of mining providing the initial materials into the sector. And then there's a long lag period before, circular economy takes over and, recycling can really take the brunt of the material supply. So in this initial phase, it's driving a lot of demand for mining. And that kind of necessitates a few things from a sustainability perspective. I guess even within this, we should recognize that there's opportunities to reduce demand. We could be more efficient with how we're using these resources still. We can explore, what that means in terms of different sizes of batteries and EVs, how much potential is there for different types of circular economy measures, such as product lifetime extension. But there's also a large recognition that we need to make sure these materials are sourced responsibly. Now, currently, a lot of the ways people are thinking about that are through voluntary initiatives, but it is also becoming more formalized and more regulated as well. And obviously, we want to minimize the impacts from mining as we scale this up. So this was a large research project that basically brought together a lot of stakeholders to the Australian battery mineral sector and a lot of Australian universities and some international partners as well. So there was myself and a large team at the University of Technology Sydney in our Institute for Sustainable Futures. We also had people from Melbourne University, the University of Western Australia, and Murdoch University who did the bulk of the research. And then we imported partners from TU Braunschweig, NEIS, Curtin University also did a lot as well. But as part of this, we're engaging with a lot of different industry partners. So we had BHP Nickel West involved in the project, the Mineral Research Institute of Western Australia, IGO, another nickel mining company. And I guess these industry partners, they all had different wants and needs for the project. But I guess there were a few messages that we kind of started the project with from the industry partners. I guess one, they were very confused by the evolving landscape in terms of voluntary standards and sustainability certifications. At the start of the project back in 2020, they were identifying that there's a lot of difficulty in actually, knowing what standards are going to be adopted, which ones should they adopt, are there ways that they can streamline their reporting against multiple standards and frameworks. And then there was also a lot of interest in improving life cycle assessment data, because some initial analysis we did showed that for the Australian mineral sector, there was actually very poor data availability. And so we wanted to improve some of the data available for life cycle assessment through the project. Now, I guess one of the major pieces of research we did was actually just systematically going through and trying to understand what all the different voluntary certifications and standards are actually measuring. and how much and I guess whether they're complementary to each other, is there significant overlap between them? And do they have different potential use cases? So, we're looking at things like the Initiative for Responsible Mining Assurance, IRMA, or other things like the Towards Sustainable Mining Standards. And we're basically saying, right, what topics or thematic areas are these addressing? What are the specific criteria that companies need to do to adhere to these standards? And then also, how do we expect these standards to drive change? And are they doing that in different ways? Now, this was actually quite difficult because as the project was going, there was a lot of movement in this space. I guess early in the World Resources Forum this year, we've heard a lot of talk about the consolidated mining standards. And that's, a very collaborative effort between both Towards Sustainable Mining, the Copper Mark Initiative, the World Gold Council, and also the ICMM. And that's a big harmonization project to try and bring together some of the standards. And so I guess that made it quite difficult as we're doing this project, just because basically the ground was moving out from under our feet. Basically, felt like every week or every month, something new popped up that we had to be aware of. But I guess we did put out some very useful guidance and reports related to this, and I'll just highlight the report on the right-hand side there that you can see, which you can find on the Future Battery Industry CRC website. Now, we also did a lot of more kind of theoretical work just to understand how different components of mine site sustainability and sustainability through battery mineral supply chains actually interact. And we did a lot of work talking to different stakeholder groups and trying to develop systems perspectives of what the various feedbacks and kind of levers for change in the overall battery supply chain are. And so what's on the screen now is just a little bit of an example of that, where we're developing causal loop diagrams to understand, for instance, how, say, transparency from investors, places pressure on other aspects of the systems. And then there's also a lot of work just to really clearly unpack what the drivers, barriers and enablers to adopting voluntary standards within these sectors are. So we did a lot of review work just to very clearly articulate what they are and then talk to people and try and understand to what extent that resonates with people. And also, are there things that, for instance, aren't in the academic literature, but all the people in the supply chain are actually saying are the really important things. So we did a lot of work just to try and understand what drives the adoption of these voluntary schemes. And then I guess related to life cycle assessment data. So there's been a lot of studies over the year looking at things like the production of lithium from Australian spodumene resources. A lot of the data in life cycle assessment databases was quite old. And there were also some literature studies which, from our perspective, were potentially misleading as well. And so our colleagues at the University of Melbourne did a lot of work to try and improve the data sets available for Australian lithium production. And so they developed new life cycle inventory data sets for some of the key lithium producers in Australia, such as the Greenbushes mine site in Western Australia. And that's basically the largest lithium producer in the world. And so to improve these data sets, there was a lot of just fundamental modeling that was done. There were visits to the actual sites, and, Cheyenne, who can see pictured there, he visited the Greenbushes mine site. He spoke to the staff there. He did a lot of fundamental and first-hand data collection just to improve the data. And so now I think we've got probably some of the, from my perspective, the best quality data for Australian lithium production now has come out of this project. And then there was also a lot of life cycle assessment work done to understand other parts of the value chain. So for instance, there was a lot of work done to understand life cycle assessment of byproducts from these production systems. Can we use nickel slags in different end use applications? And so those types of things. But I guess just to kind of sum up, so we did a lot of work looking at just the idea of responsible minerals. What does that mean? How do you demonstrate that in the market? And as part of that, we did some work with companies as they were actually trying to adopt some of these schemes, and we're interviewing them throughout the process of them actually adopting some of these voluntary schemes. And that basically revealed that it was very time and data intensive. So we think the large players can adopt these without too much effort. But for instance, small exploration companies, they're really going to struggle to adopt some of these voluntary schemes. And so I think there needs to be better pathways for them to do that. With life cycle assessment, we saw that we were able to improve the data sets available for Australia. There are still data gaps and there's still commodities that need to be assessed in the future. But I think that's gradually improving. And then just from a broader circular economy perspective, we've also seen in Australia that the Australian government has basically a strategy around circular economy. There's been a circular economy framework developed. And I guess for the battery mineral sector, a lot of this is being translated into how do we basically use byproducts better? Are there different ways we can reutilize our byproducts in different applications? Can we put, for instance, slags from copper production or nickel production, can we use that in road base? Those sort of things. Can the lithium tailings be used as pozzolanic material to improve the performance of concrete? So we went through and we kind of systematically looked at all of these options. So I know that's kind of a lot to take in, but if you've got any questions, please feel free to reach out to me or anyone else involved in this research, and we're always happy to talk more about it. Thank you.
Thank you, Stefan. We don't see any burning question yet in the chat or other questions in general. So we continue with the last presentation, and then we open the floor for all the speakers. Is that okay? So now, please, we welcome the last speaker, and the person has already arrived. And
okay.
Welcome, Feven Desta, and from Delft University. And please, the floor is yours. You have 7 minutes, max 8. We still need to. We want to have questions from the audience. Thank you.
Thank you, Sonia. Good morning, everyone. My name is Feven Desta. I am an assistant professor in the section of resource engineering at TU Delft. And the topic of my talk is unconventional sources as a strategic pathway for future resource security. The global demand for mine products, including the critical raw material, is rising due to population growth, the economic expansion, and the imperative of transitioning to green energy. This signals prosperity and the urgency of decarbonization, which is good. However, it also implies that we need a large quantity of minerals, and most of them are identified as critical raw materials. The other presenter already gave detail about the critical raw materials, so I will skip that part and go to the next slide, please. Could you? Yes, to put the demand into context, let's take one particular example, the wind turbine, which is one of the clean energy technology that potentially enable the energy transition. To build one single wind turbine that could potentially generate 3 megawatts, we need about 4.7 tons of copper. And that's not the only metal we need. We need rare earths, aluminum, and all other elements. So what are the challenges? Next slide, please. The challenge is the need for raw material is increasing as technology advances, and it's also expected to increase exponentially over the coming few years, as you know. So it also implies that to cope up with the growing demand, there is a need for strategic approach to, next slide, please. Strategic approach for the diversification of the supply sources. So for that, we need to consider alternative sources from the primary extraction. For example, because resource distribution is not uniform, we cannot mine everywhere. So one strategic solution could be to look at mine waste sites. Next slide, please. Mine waste sites. For example, mining involves different activities, and these all activities generate different kinds of waste. As you can see here from this slide, the one which is highlighted in red are potential. They are waste dump sites with a potential for containing metals of economic interest. Now, the interesting question is why we expect metals of economic interest in the waste piles. Could you please go to the next slide? There are multiple reasons for that, and some of the reasons, it's a combination of factors actually. One is like the historic context, and the natural factor, the geology, material co-occur together, and in the past, mining focuses on extraction of one commodity, and then all the other commodity will be dumped as a waste. And also natural processes like weathering and erosion could also accumulate these metals of economic interest, including CRMs, in the waste material. The other reason is the efficiency of recovery techniques or processes, which are not that efficient enough. Still, they leave those metals of interest in the waste. And technological and economic drives also makes now more feasible to extract this metal from waste. For example, if we take certain commodities like lithium, in the past it had low economic value. As technology advanced and its importance now in battery industry, for example, make it one of the most important economic CRM. So these are the drivers and also the reasons why we find metals of economic interest in the waste piles. Next slide, please. Just to show you the potential of economic value in the waste pile, according to this study, which you see here, this is done by Global Tailing Review, and according to the Global Tailing Review, there is about 282.5 billion tons of tailing worldwide. This is based on 8,500 tailings. And in another study, it's estimated that the value of precious, critical, and strategic metals contained in tailings worldwide is estimated to exceed $3.4 trillion. So there's a huge economic potential in this waste piles. This is one waste stream, the tailing. Next slide, please. There are multiple benefits of remining or secondary recovery from mine waste. For example, it could somehow contribute for security of resource supply, and we can generate revenue, so it has economic benefit. And also, when we remine from waste pile, we are minimizing the environmental load of this waste to natural and human environment. For example, we are removing these toxic metals and also the other metals from this waste pile and minimize the footprint of mining activities. And also it ensures resource efficiency, and it fits with the concept or principle of circular economy, because we are maximizing the value of resources already within the system. And in the future also, it could potentially reduce the need to open new mines. However, next slide, please. There are challenges associated to that, which we need to overcome to realize the extraction of these metals from the mine waste. Next slide, please. There are multiple challenges. Here I have some of the challenges. One, the nature of the material. They are very heterogeneous and dynamic in nature, and there is no geometric control like primary deposits. And in most cases, the concentration of this metal could be lower than the primary source. So we need some sort of technological advancement for accurate characterization of these waste systems. And we need to understand it from multiple scale perspectives. So we need multi-scale modeling, spatial-temporal analysis to understand the dynamics there. And also remining could also pose some environmental problems. So we need to come up with a mechanism for proactive management of this mine waste from the remining activity as well. Next slide, please. I have a few examples for you to show you the application examples in our group. What we are doing is by utilizing different sensor technologies and data analytics, we try to understand the composition of this waste site and the possibility for recovery. I don't have time to go more in detail in this, but we deployed infrared and XRF technology for this specific tailing site to understand mineralogical distribution and the possibility of detecting these critical raw materials. And it was possible to detect titanium, manganese, yttrium, and vanadium as an example, some of the critical raw materials, and also other metals of economic interest as well. So there's a very good potential at this site for recovery. Next slide. We have also investigated slag material from ferronickel slag, and where we deployed laser-induced breakdown spectroscopy and infrared to understand the mineralogy and geochemistry. And also here, I want to emphasize that slag material could crystallize with different grain sizes. So the first question we have was, is there compositional variability within this grain size? We haven't found geochemical differences. However, there is mineralogical difference within this grain size, and that has implication for a recovery. However, from the technique used by deploying these technologies, we were able to detect vanadium, cobalt, titanium, and nickel in this slag material with interesting concentration amounts. Next slide, please. The other waste stream we have investigated is West Rock Pile, which is found in Spain, and we tried to explore the mineralogical and geochemical composition, their spatial distribution. And here again, in this site, at this site, we were able to detect some of these elements of economic interest in the West Pile, and their distribution could be variable. There are multiple reasons for that. However, the key point is there are these CRMs and other metals of economic interest in the West Pile. A spatial distribution is very interesting to see. They might accumulate with influenced by different natural processes. And the key takeaway is that in terms of mineralogical assemblage, there could be variability that could be attributed to different reasons. However, it's possible to detect these metals of economic interest. Before I come, next slide, please. Before I conclude my presentation, I would like to highlight a few key points. One is to ensure sustainable supply of resource, we need to diversify our supply sources. And mine waste could be an alternative future resource. And technology, sensor technology and data analytics could potentially enhance our understanding of this mineral potential to explore it more in 3D and even in 4D, incorporating the time aspect of it as well. Economic viability of rare mining, yeah, that requires a study and it's site dependent, I would say. However, there's a great potential for depending on the site condition. And there's ongoing technological development happening now in terms of resource extraction and material characterization. And I believe this drive efficiency and viability in the remining business. And also this requires multidisciplinary approach because we need to understand different systems here. For one is advancement in material characterization technology. The other one is advancement in the extraction or the recovery technology. So we need to see it from multidisciplinary approach. Achieving this could have like significant future impact. One is we will be able to diversify the supply source. The other one is we can reduce potential environmental impact from the historic waste pile and also from current mining activity. We can minimize the waste mode, the waste impact. And in this way, we will promote efficiency and resource utilization, and also we can contribute to the circular economy principle. Having said this, I conclude my presentation. Thank you for your attention.
Thank you all presenters. So with this, I open thank you, Fiven. This is for the last presentation, and I open the floor for more questions. Maybe I can kick off with one or two questions, and then please we read them in the chat. I also have I'm collecting the ones in the chat. Juan Pablo, I would like to ask you on the cost aspect. Could you elaborate, maybe comparing with the closest alternative? What about the economic advantage of your technology?
Sure, Sonia. Sure. Yeah, thank you for the question. We have typically this type of question. Basically, what we are trying to substitute are portable batteries. So the most typical ones are kind of a coin cell batteries or the typical alkaline with a cylindrical form factor. And our value proposition is that we try to fit the demand. So if we focus exactly on the type of use for these single-use devices, our batteries are very competitive in terms of performance and cost, and obviously in environmental sustainability. So we can meet the same cost as the typical commercial alternatives that have been in the market for decades, and it's already a very mature technology. So our disruptive technology is already can already match this in terms of cost if we focus on the actual use of the energy and the materials that the batteries need to provide.
Thanks. Thank you. One question is from Stefan Fitch, and it's about, it would be for Fiven maybe. You can try, Fiven, please, to answer on this. How high do you estimate the potential of circularity to decrease the projected shortfall of many critical raw materials in Europe? You provided a solution, an approach. Maybe you can elaborate to your best, knowledge or understanding. Please.
Yeah, okay. Yes. The potential, if we ask like what is the potential for recovery, for example, CRM from historic mine waste in Europe, the potential is significant. For example, according to the European Commission, there are over 1,100 mining waste facilities registered across EU member states. And Europe has a long story of mining. Many areas, particularly in countries like Sweden, Finland, Spain, and Germany, have numerous historical mining sites, including waste rock piles and tailings. And I would say the potential is significant, driven by Europe's need for raw material security and the critical need for CRM independence, the autonomy. And also, there is also environmental restoration goal, which is getting more attention, and this remining from this waste could significantly support this restoration efforts. And also now we see advancement in technology from the recovery perspective, technology from characterization and modeling. So if we sum up all this, there is a great potential, but to realize it, of course, we need support also from regulation or policy perspective. Now with the Critical Raw Material Act also, diversification of the supply sources recognized as one potential solution. So my answer would be there is a great potential, but still we need to advance it and understand it in a way we need to know how much of this resource do we actually have in the market, I would say.
Thank you, Fiven. There is another question for you in the questions and answers part. Maybe if you could try to elaborate on that. And now I have a point for a question for Stephen. And it was an impressive work you did on the comparison of standards, sustainability standards in the mining sector. So, of course, please request, could you provide 1 or 2 links of the key publications you have produced in the chat for the audience now? But also my question was on what is your recommendation, especially for those that are interested in choosing one or the other, where to start, which criteria to consider before entering into implementing or using one or the other standard, and linked as a complementary point, how do you see the standard on the standards on recovering secondary materials today fitting? So thank you.
Yeah, so I guess we're mostly looking at standards that are mostly applicable to primary production. So yeah, mostly the standards focus on mining and then also smelting and metal refining. And I guess I think it depends whether you're a producer or you're a consumer. So I think if you're a producer, there's basically two types of standards I'll be thinking about. So I think my perspective would say the consolidated mining standard, the ICMM and others are developing at the minute. To me, that's meant to be a very inclusive standard. They're trying to get as many people on board as much. And I think my understanding of the theory has changed is, that's designed to basically lift the bottom performers to a minimum threshold of performance and responsible management. Whereas, the other things like the Initiative for Responsible Mining Insurance, from my perspective, it partially does that, but it enables the better performers to justify an even better performance. So I think one is kind of raising the bottom, and I think the other is providing a pathway to demonstrate overperformance. Yeah, and so I guess when we look at, say, the car manufacturers, like for instance, if you look in Tesla's sustainability report, they talk about, wanting to preferentially purchase, for instance, from IRMA certified mines. So I think there is a bit of demand from the consumers and the manufacturers, but it requires that transparency, the information along the supply chain. And so there needs to be better ways to actually communicate it along the supply chain. So I feel like I didn't quite answer your question, but yeah, maybe that's some useful context for people.
Yeah, thanks. And now answering to one of the open questions in the question and answer part about graphite, synthetic graphite as an alternative to CRM. Thanks for clarifying that this is carbon intensive. I think this is a main argument. So we should not just think as a black and white solution. This is the solution, but consider that this is a carbon intensive alternative. Thank you for clarifying that. Maybe we check another open question, and that this maybe the last one we can cover, that is for Fiven Desta. It's about the need to acknowledge that sites producing raw materials from waste rock, sludge, tailings, or slag will resemble in most of the important ways, social considerations, environmental, they will resemble in the impacts in several key aspects. Do you agree, Fiven, that we have commonalities to take into account?
Yes, I absolutely agree with this idea. If the secondary recovery or remining requires environmental permit, that takes into account social license, community consultant involvement, and long-term environmental impact assessment also, and mitigation strategy. And I also believe that transparency and accountability has to be clearly communicated, and reclamation and rehabilitation obligation has to be fulfilled. We know there's an issue. People don't want to have like mine, not in my backyard, is one of the most challenged here in Europe. It's actually recognized. However, with involvement of the community and also with transparency and accountability, I think, and also the need and also awareness plays a crucial role in my opinion, knowing that, okay, we need phone, but like we need to source the material from somewhere, and resource distribution is not even. We just have to deal at the location where we find the resources. This is very important concept that needs to be disseminated across the society, and also we need to make sure that environmental permit is there to do the secondary recovery or remining. So I absolutely agree with your comment there.
Thank you. And with this, allow me to provide the concluding remarks of this session. It was very interesting. There are several takeaways, but 2, 3 for me would be there are definitely options for recovering more of what we need. We were talking about critical raw materials, but we need, of course, to be careful on considering the trade-offs. That is one point. So let's go for careful assessment and implementation of the measures. If we were investors, we should do that. Second point, collection is crucial when we want to recover from from products, no, that have been used and that can contain these critical raw materials, and collection is critical everywhere. Without collection, we will hardly have the minimum scale for cost efficient and good quality recovery of these materials, probably. The third point is there are also recommendations in standards, in documents, authoritative or from associations that guide us with criteria. So we should go for that. It's not that we are lacking information, it's maybe just knowing where they are. And I invite you to continue this exercise and communicate to your producers, policymakers, stakeholders about these opportunities and the way forward, not just looking into the issues and problems, but also into the opportunities that we have. And thank you very much for sharing this with us today.